Hi, my name is Goestchel and I'm gonna present you part of my PhD work. I work in a acoustic lab in France, which is focused on environmental acoustics, and the work I'm gonna present you today is about numerical method for outdoor sound propagation, and I'm gonna focus more on numerical dispersion effect related to this method. I would have really liked to be here in person, but I couldn't, so I hope you will still enjoy this video. First, I'm gonna introduce you and give you some context about my research. Then I'm gonna talk to you about the numerical method in itself. Then I'm gonna go through all the numerical experiments we've done on this method. I'm gonna present you the results, and I'm gonna go to a conclusion and some perspectives. So for the context, we study environmental acoustics in order to protect the biodiversity, and also because it's a physical problem interesting as itself, because it's multi-scale, it involves lots of scatterers, and it's mainly impedance boundary conditions. In this medium, it involves various sources with a lot of bandwidth and wavelength diversity. And we do all this work in the frame of a European directive, which stands for the protection of quiet areas. In this topic, so we use numerical methods to model sound wave propagation, and I'm going to give you some history about the method we use, which is called the transmission line matrix. It has been used at the beginning for electromagnetic uh, modelization, as most of the acoustics numerical method. It's a time domain method, and in our lab it has been validated and studied for room acoustics, propagation in urban areas, and the last PhD student who worked on it did propagation through parallel cylinders above an horizontal plane, because he wanted to compare his modelization to lab simulation of trunks, but perfect cylinder in this case. The advantage of this method is that it's already developed in the lab and parallelized on GPUs thanks to a Python OpenCL frame. Then the good part is that it's also simple to understand this method, because it's based on the Huygens principle and the wavelet decomposition within it. And the main principle is that you have a point source here, and it emits an impulse of pressure going to another node, and this node will re-emit pressure pulses with a reflection and a transmission coefficient. So this is the core of the method, and it all comes from it. Then starting from this core, we can also go to a more classical pressure scheme, which is really similar to FDTD. In this case, from this pressure scheme, we can link this method to the wave equation. And you can see here that this method is order 2 in time and space, and that the propagation speed is related to the discretization of the mesh, so delta L here and delta T. However, going through this theoretical aspect, it's possible to show that the method is dispersive and present axial dispersion on the main axis of the mesh. And this is this property that we want to study, because the fact that this method is order 2 also means that this method boundary condition will require less order and less nodes and less complexity than higher order method like FDTD order 4 or um, finite elements method. But so we keep our interest in this method because of the boundary condition. However, it is dispersive, and we want to know what will be the effect. The dispersion effect of this method is like any other else, and it's highly related to the number of points per wavelength. If you take a sine and discretize it with 10 points, you will get a discretized sine. But if you only take 3 points per wavelength, you will get a flat line. This is a common principle. And now you can see the effect of the dispersion on one wave packet. And you can see that on the diagonal here, there is no dispersion, and here there is dispersion. So that's the effect that dispersion can have on a signal, which is not wanted, but we will see that sometimes we can cope with it. To assess on this effect, we did two numerical experiments. The first one is in free field. So we had like two lines of microphones. The first one is horizontal and the other one is diagonal. And you can see on the specification that this is made for sources with maximal frequency of 2400 Hz and 10 points per wavelength at this frequency, and the maximal radius from the source is 450 meters. This configuration is indeed quite demanding, and it's like 3000 wavelengths and 50,000 per 50,000 element, spatial element, and anyhow it takes not that much time of computation, but the memory needed is quite heavy. Then we did a reflection experiment to assess the effect of dispersion on a reflection. So here you can see the source and a surface with a perfect reflection boundary condition, and a matrix of receiver, which is a polar matrix, because we want to assess the effect going from the source to further away. And then we assess the normalization of all this microphone with the standard deviation radio, because we compare all the signal to an analytical solution, and we want to be sure that for the first microphone the energy received from the source is equal to the analytical solution, so that's why we normalize. And then the main physical quantity we want to evaluate, because it's really meaningful in our domain, is attenuation compared to the reference microphone. So the reference microphone we placed is the first one here, and this is how we compute it with the microphone considered and the first microphone of the line. Then you can see here the last simulation time step. This is the result for the free field. So the main conclusion is that the higher in the frequency we go, the higher is the error. You can see for 2000 Hz, we have 1.25, 1.5% of error on the group speed of the wave packet, and here it's like nearly 2% of error on the group speed, and you can see that it's mainly for close to 10 points per wavelength, and the further away from the source. For the reflection results, we have here for the Gaussian pulse, and you can see that for a Gaussian pulse, the error on the polar matrix is not that high and really not relevant. However, this source has a particularity, is that it's over discretized, and actually for the maximal frequency, and here 10 points per wavelength, we don't have a lot of energy, and most of the source energy is really over discretized. Most of it is over 100 points per wavelength. So then if we take a more harmonic source here with most of the energy centered on the maximal frequency, you can see that we get huge discrepancies between the numerical simulation and the analytical solution. So here it's in more detail why we have these discrepancies, and you can see at this angle that the peaks of attenuation are misplaced. It's due to destructive interference and especially displaced destructive interferences. And then here at 10 degrees, it's not that much the case. And here again, for this angle, we have a large displacement of the attenuation peak, which is not wanted. So to conclude, the 10 points per wavelength criterion is really not sufficient, and it should be used with care, even though it's really used in the literature. Then what we want to do with this method is compare it when we model complex scenarios, because we do model more complex scenarios than the one I showed in this presentation. To want to be able to validate this modelization with in situ measurements. So maybe then we have the opportunity to change the scheme or increase the order. And we want to integrate wave in complex media theory, because it would be nice to have effective medium with effective wave number and speed. And in the end, it would be nice to have MPI parallelization to be able to increase the number of points per wavelength and the simulation. So here you have some bibliography, and thank you for listening. I hope you enjoy